This is the second video for section 1.7, 1.7.2, differentiability at a point. So we will say that a function f of x is differentiable at the point x equals a if the derivative exists. So if f prime of a exists. So in this video we're going to look at the relationship between a function being continuous and a function being differentiable. So notice that a function being differentiable, saying that the derivative exists at a point, we know geometrically what that means. It means that there is a unique tangent line to f at a. And when mathematicians say unique, they mean exactly one. So there is one and only one tangent line to f at a if f is differentiable. So one way to understand this definition is to think about when does a function fail to be differentiable. And the first way in which it can fail to be differentiable is that the function could be not continuous or discontinuous at a. If a function is not continuous at a, then a function is not differentiable at a. And the reason is that there would be no well-defined tangent line at a. And you should think through that. Think of all the ways that a function could fail to be continuous. You couldn't draw a single well-defined tangent line at any of our discontinuous functions at a. So those are not differentiable functions. Now, what if I have a continuous function, but now instead of, now at a, I have either a corner, a cusp, or a vertical tangent line. I claim that those are going to be functions that are continuous but fail to be differentiable. So let's see a few examples. So here's a graph of the function, the absolute value of x plus 1. So this has a corner at x equals 0. And notice if I try to draw a tangent line from the left-hand side, it looks like it has maybe a slope of -1. And if I draw one from the right-hand side, it looks like it has a slope of 1. And in particular, both of those would be valid choices for my tangent line at 0. So since I cannot draw one and only one, we say that the derivative does not exist there. So f is not differentiable at 0. Another example, which is useful to see, is a function of the function f of x equals x to the 2/3. So this function, which you may or may not have seen much before, this has a vertical tangent line at x equals 0. So right there at x equals 0, the tangent line is vertical. And what does that mean in terms of slopes of lines? Well, slope of a vertical line is undefined, so that means f is not differentiable at 0, because if the derivative is the slope of the tangent line, and the slope of the tangent line is undefined, that means f prime is undefined. So vertical tangent lines are no good in terms of differentiability. And neither are corners. Cusps fail for the same reason as corners. You have different possibilities for tangent lines as you approach your cusp. So both of these examples show that just because a function is continuous at a, it does not necessarily mean that the function is differentiable at a. However, it is a fact that we'll talk about in class that if f is differentiable at a, then indeed f must also be continuous at a. So what we say mathematically is we say differentiability is a stronger condition than continuity. That means if I'm differentiable, I'm definitely continuous, but not necessarily vice versa, as those two examples before showed.